Okay, so next we'll describe hidden Markov models, which, as we'll see, are an instance of the generative modeling approach that I just described. So in hidden Markov models, the basic idea is the following. I have some input sentence x, which consists of n words. So each of these is a word. You know, this could be the, dog, and so on and so on. And I have some tag sequence y1 through yn. So this might be determiner, noun, and so on. And an HMM is going to define a joint distribution over over word sequences paired with tag sequences. So this is precisely an instance of the generative models I just showed you, in that if we think of a word sequence as an input and a tag sequence as a, quotes, label, we now have a joint distribution over these things. And this is a distribution over all possible word sequences x1 through xn and all possible tag sequences y1 through yn, where these two sequences have the same length. Once we have defined a model of this form and learned the parameters of this model from a set of training examples, the output from the model is going to be the, so here I have an input x, which again is a sequence of words. The output for this sequence is going to be the sequence of tags y1 through yn, which maximizes this joint probability. So here I'm basically going to have a search over all possible tag sequences for the input sentence. I'm going to find the tag sequence that maximizes this probability. Now, this in itself is an interesting problem because the number of possible tag sequences grows very quickly with n. It's exponential with n. And so brute force search over all possible tag sequences is in general not going to be possible. But we'll see there's a very nice way around that problem for the class of hidden Markov models. Okay, so on this slide I've given a formal definition of trigram HMMs. So here I have the formal definition, and on the next slide we'll see an example which will probably help to clarify things. But let's go over this definition. I'm going to assume two sets. So V is going to be the set of possible words in the language. So it might contain, for example, the, dog, cat, a, box, and so on and so on. And I'll use S to refer to the set of possible tags. So for example, we might have determiner, noun, verb, preposition, adverb, and so on. Typically, by the way, we might have, I don't know, on the order of a few tens of tags. The Wall Street Journal part of speech tagging corpus I referred to earlier had approximately 50 tags. It can vary quite a bit by corpus and language, but that's not a bad estimate. Okay, so we have these two sets, and then a sentence is a sequence of words x1 through xn where each xi is in V, and a tag sequence is going to be a sequence of tags y1 through yn plus 1, through yn plus 1, where yi is in S for I equals 1 to n, and yn plus 1 is stop. Okay, so I'm again going to make use of this stop symbol, which we saw in the previous lectures on language modeling. And it's going to play a very similar role to what we saw in language modeling. So I've just extended our definition here. So our joint distribution is now over sequences x1 through xn, together with tag sequences y1 through yn plus 1. So this might, for example, be the, dog, box, and this might be determiner, nn, VB, stop. So notice I have this extra symbol at the end of the tag sequence. So how do we define this joint probability? So I have a product of two terms here. Here I have a product from I equals 1 to n plus 1 of qyi given yi minus 2, yi minus 1. Notice that this is very, very similar to what we saw in trigram language models. In fact, this, as we'll see very soon, is basically nothing more than a trigram model applied to tag sequences. So that's the first term. And the second term is as follows. I have a product from I equals 1 to n of e xi given yi. So the e parameters, for example, look like the following. We might have e of the given dt. And that basically corresponds to the probability, given that I have the tag dt, that I see the word there. So in some sense, it's the probability of the tag dt emitting or generating the word there. Okay, and I have one term for each word in the sequence. So the parameters in the model are as follows. I have a trigram parameter for every trigram of tags UVS, where U and V can be in the set S, and I'm again going to use the start symbol star. This again is very similar to what we saw in language models. And S can be any member of S, or it could be the stop symbol. So that's the first set of parameters. These are basically trigram parameters. And secondly, for any word in the vocabulary and for any tag S, I have the conditional probability, or rather parameter corresponding to the conditional probability of X given S. These are often referred to as emission parameters. So two parameter types in the model. Given these parameters, I can then calculate the joint probability of a word sequence x1 through xn and a tag sequence y1 through yn plus 1 as this product of two terms. So that's all a little abstract. Let's go through a concrete example to illustrate these definitions. And here I've assumed that the sentence is the three words, the dog laughs, and the tag sequence is dnv stop. So D for determiner, N for noun, V for verb. How do I calculate the probability of this word sequence paired with this tag sequence? So by the definitions on the previous slide, it works as follows. So firstly, I have a product of Q terms, and notice for each tag here, dnv stop, I have an associated Q term, qd times qn times qv times q stop. And at each point, I'm conditioning on the previous two tags. So these star symbols are in a very similar way to what we saw with language modeling. They are sort of initial sequences, initial symbols at the start of the tag sequence. So I have D given star star, I have N given star D, I have V given Dn, and then finally I have stop given NV. So those are the Q parameters. And then in the second part of this expression, I have a product of E parameters, one for each word in the input sentence. So I have E the given D, that's for this word here. E of dog given N, that's for this word here. And finally, E of laughs given V for this word here. And intuitively, these parameters correspond to the probabilities of first generating the word the from der, D, then generating the word dog, given the underlying tag is N, and finally generating the word laughs, given the underlying tag is V. So remember, the name of these models is hidden Markov models. Let's just think a little bit about why they actually get this name. And it'll also help us develop a little bit more intuition for these models. So this product of Q terms is essentially a prior probability over tag sequences. So this is the probability of y1 through yn plus 1. Remember, in the noisy channel model, we usually had pxy is equal to p of y times p of x given y. So these q terms correspond precisely to p of y, where y is now an entire tag sequence. And this is a second-order Markov chain. So we've basically just applied the idea of Markov models to this problem of defining p of y. This is exactly the same as the form we saw for trigram language models in the previous part of the course. Okay. So if we look at this expression, this is actually the probability of x1 through xn conditioned on y1 through yn plus 1, where we're basically assuming that each word xj is chosen depending only on the value for yj. So we've made some fairly strong independence assumptions here that each word only depends on its underlying part of speech tag. So this leads to the name hidden Markov models. In some sense, this is a Markov chain that is hidden, in the sense that you can think of a generative process where we first choose a sequence of tags under this model, and then for each tag we generate an associated word, x1 up to xn. These xj's are observed, and these tag sequences, the y's, are unobserved. And the problem on a test example is the following. I receive a sequence of words, x1 through xn, and I have to find the most likely sequence of tags underlying those words, y1 through yn plus 1. So I have to recover the most likely settings for that hidden sequence.